Thank you, everyone, for coming to my talk. I'm going to be telling you a tale of binary translation. So first, a small introduction about myself. I'm Amanieu D'Antras. I'm a member of the Rust library team and library API team. I've also the leader of the Inline Assembly working group for the Rust language. You may also know me for some of my crates like Hash Brown or Parking Lot. I'm working as a consultant for Huawei's Trusted Programming Lab, who's sponsoring me to work on the Rust compiler and standard library. I did my PhD at University of Manchester on binary translation and subsequently founded a startup which is developing binary translation software for ARM systems. So you can, here's a QR code with a complete version of all the code that's going to be presented here. There's also a copy of the slides. For those of you at the back of the room, you may want to grab a copy because it may be hard to read the text. I will post a link again at the end of the talk. So let's start with a bit of background. We need to talk about CPUs. So modern CPUs can be quite intimidating because they have billions of transistors and do all sorts of very complex stuff. But fundamentally, what a CPU does is very simple. The CPU sees memory as an array of bytes. That's it. And has some registers, which you can think of as local variables within the CPU. So the CPU basically reads some instruction bytes from memory, decodes them into an instruction, and then it will perform whatever operation is described by this instruction. So operations are typically add the value to registers together and put the result in another register, or load some bytes from memory and put them in a register, take a value in a register and write it to memory. Once that is done, the CPU increments the program counter, which is a special register that holds the address of the next instruction to execute, and then it goes on to fetch next instruction, executed, etc. So one thing you'll notice is that in this example, we have a 32-bit CPU, which really means that the registers are all 32-bit values. The program counter is 32 bits, and the memory has 2 to the power 32 addresses, which basically means there's 4 billion bytes that you can access. This will become relevant later on. So an instruction set architecture is basically the language that a CPU speaks. It describes how bytes are interpreted as instructions and basically tell the CPU what to do. This also includes, so the instruction set architecture also includes details about how many registers the architecture has, how big the address space is, etc. You may have heard of some of these: ARM, x86, PowerPC, RISC-V, MIPS. And what we're going to talk about in this presentation is binary translation, which is we want to take a program that's been compiled for one architecture, so that it's a bunch of machine code that is in the language of one type of CPU, and run it on a different CPU that understands a different architecture. For those of you with the fancy new ARM MacBooks, this is basically what Rosetta 2 does to run your x86 applications on an ARM CPU. So let's focus on RISC-V. RISC-V is an open standard instruction set. which basically means that if you want to build a RISC-V CPU, you don't need to pay a license fee to anyone. The basic version of RISC-V is called RV32i, and it's a very simple architecture. It only has 39 instructions. Very simple, especially compared to some of the other ones, which can have up to thousands of instructions. RISC-V also has many extensions, which add extra instructions and features like floating point 64-bit addresses, but we're not going to cover them in this talk. So RV32i, the base RISC-V instruction set, has 32 registers called X0 to X31. Each of them is 32 bits. The only special thing is that X0 is always has a value of 0, and any attempts to write to it are just ignored. This is mainly an instruction encoding trick to allow to basically reduce the number of instructions needed by the architecture. For example, if you want to if you want to put the value 5 in a register, what you do is add 5 to X0 and put the results in whatever register you want. So this is how RISC-V instructions are encoded. Each instruction is 4 bytes, and the details are basically encoded as bit fields. The opcode determines the instruction format. The opcode plus the function determine what the instruction does, whether it's an add, subtract, load, store, etc. RD is the destination register. RS1 and RS2 are the source registers. Some instructions have an immediate field, which is basically a constant value that is directly encoded in the instruction instead of having a value come from a register. So here are the actual RISC-V instructions. On the left, you have the assembly code format, which is a text representation of the instruction. So, and on the right side, you have the actual operation that's performed by the instruction. So you can see you have an add instruction, which takes a destination register and 2 source registers, and just adds the values in those registers and places the result in the destination register. Same with subtract, XOR, OR, and shift left, signed and unsigned shift right, and an instruction called set if less than, which does a signed or unsigned comparison, and depending on the result of the comparison, sets the destination register to 0 or 1. So these instructions take two registers as input. There's also instructions that take a single input register and a constant. And you'll notice they're basically the same. The only missing one is a subtract instruction, because just you can do the same thing with an add and just negate the constant. Other RISC-V instructions are the load and store instructions for reading and writing to memory. Since registers are 32 bits, loads from memory have both signed and unsigned variants, which either sign extend or zero extend the loaded value. Store instructions also fairly straightforward. The address to read or write is calculated by adding the immediate to the first source register. More instructions are branch instructions, which compare two registers using a signed or unsigned comparison. If the result of the comparison is true, we just jump to, we set the program counter to a particular value, which is where we'll essentially jumping execution to that target. If the comparison is false, we just continue on to the next instruction as normal. There's also jump instructions, which unconditionally jump to a target address, but can also save the address of the next instruction to a register. And this is used for function calls where you want to save the return address somewhere so that the function that you're calling knows where to return to. Finally, we've got a few miscellaneous instructions. LUI is used to generate 32-bit values. Because the immediate values and instructions need to fit within 4 bytes and so have space for the actual opcode, you can't actually represent all possible 32-bit values. So you need 2 instructions using LUI to generate any 32-bit value. LUI stands for load upper immediate, by the way. AUI PC, add upper immediate to PC, is similar, but also adds the current program counter value. And this and the jump and link instructions are basically the only 2 ways to read the program counter. Finally, we have eCall and eBreak, which are a prayer to a higher power. They're basically used to, they're usually used to invoke an action from the operating system or a debugger, something outside the current execution environment. So, unfortunately, the CPU on my laptop is x86 and doesn't actually understand RISC-V code. But I still want to run a RISC-V program. What do I do? Well, let's write an emulator that simulates the execution of a RISC-V CPU. So the first thing that we want to do is represent the state of the emulated system. So in this case, we have the CPU state, which is the registers and the program counter, and the memory, which is an array of bytes. We're emulating a 32-bit system, so there's 4 billion possible memory addresses, and we add an extra 3 bytes of margin just in case you try to do a 4 byte read or write to the very last possible address. And it allows us to avoid any bounce checks. It just makes everything else much simpler. When we start the emulator, we're going to load a program into this memory. Program's just a bunch of bytes. And we're then going to start executing the program from address 0. So the actual emulator has 3 stages that are executed in a loop. First, we fetch an instruction. We just take the program counter, read 4 bytes from that address in the memory, and then build a U32 out of that. We also keep track of the address of the next instruction because we're normally going to go straight to execute the immediately following instruction afterwards, unless the instruction we just fetched is a branch or jump instruction, in which case the next PC might be overwritten by a different address. Then we need to decode the instruction. It's relatively straightforward. So first we use a helper type instruction bit fields to just extract the various bit fields of the instruction. It's not very interesting. It's just some shifts and masks. The first thing we do after that is to match on the opcode field, which determines the instruction formats. Once we've figured out the opcode, in this case, this opcode is a register, arithmetic, or logical instruction. Then we match on the function fields to figure out the exact operation that this instruction represents. Add, subtract, etc. And finally, we execute the operation. So execution is also relatively straightforward. If we have an add instruction, we just read the 2 input registers from the state, add them together, and write the result to the destination register. setReg is a small helper function because remember, register 0 always has the value 0, so we need to not overwrite it. Loads and stores basically calculate an address and then read and write to the memory at that address. Branches and jumps just update the next PC variable. ECall invokes a special handler function. In this case, since we are the higher power, we will just define some utility functions that the emulator can call, such as printing a string to memory. And what is the very first string that we're going to print? Hello world. So this is a very simple hello world program. Just sets up some registers with the parameters for the system call, invokes a system call, and then we've defined the eBreak instruction to terminate the emulator. You may notice some of these instructions are not in the list we've covered before. They are actually assembler shorthands. It's basically, they only exist at the text level representation, so li is basically add some constant value to x0 and put that in the destination register. La is just load address. So we just build our example program with Clang, convert it to a binary file that can be loaded directly by the emulator, and then run it. And it works. Yay! So now here's the part that we really care about: performance. Let's look at the performance of the emulator. On the left is the code that calculates the nth number in the Fibonacci sequence using a loop. It's fairly straightforward. You have the inner loop here is 6 instruction, and this loop is executed n times. So let's try and find the 1 billionth number in the sequence. First of all, first thing to notice, this number is actually wrong because we have overflowed many times. This is technically the low 32 bits of the billionth number in the sequence. But this doesn't really matter because what we care about is performance, not correctness. So our main loop has 6 instructions. So we're executing about 6 billion RISC-V instructions. However, on my machine, so using the perf tool, we can see that 321 billion instructions, x86 instructions, are executed. That's about 50 x86 instructions for each RISC-V instructions. That's terrible. And the main reason for this is that every time we're executing a RISC-V instruction, we have to run the decoding process all over again. So what do we need? Well, the emulator we've got so far is called an interpreter, and they're easy to write, as you've seen, but they're quite slow. So to improve the emulator, what we need is a JIT compiler. So here's our main loop again, 6 instructions. And what we really want is the code that's on the right side. There's no decoding, it just directly performs the operations on the emulated state. So it just reads values from the state directly, adds them, subtracts them, etc. So how do we actually get there? Well, first of all, we need to think about how are we going to build this JIT compiler? Problem is, building a JIT compiler is hard. Who would have known? Solution, other people have written compilers before. So let's just use RISC-V. So here's how this new emulator is going to work. First, we're going to check if at the current PC we have a translated function. If not, we're going to collect RISC-V instructions and turn them into Rust function, like I've shown on the previous slide. Then we're going to compile this Rust code into a dynamic library. Then we're going to load that dynamic library, get a function pointer from it, save that function pointer in a hash map for step 1, and then call that function pointer. And this will basically emulate the effects of those instructions on the state. Rinse and repeat. I'm so sorry. So how do we actually generate the RISC code? Well, we don't want to have to duplicate all of the work we put into our instruction decoder. So what we are going to do is split our code into a generic front end, which is responsible for instruction decoding, and a back end, which is responsible for either executing the code or generating translated code. So the trans trait is the interface between the front end and the back end. The key idea is that we make a distinction between a runtime value and a compile time value. So as you can see from here, the value is an associated type, and all of the operations just consume and return this value type. Some operations, so here's the rest of the trans trait. Some operations don't use value because they're compile time operations, like the current program counter address and setting the next program counter address. These need to be done at compile time because we need to know which instruction to translate next. However, the jump operation operates on the runtime value. We don't know where it's going to jump to. It can be a target that's not known at compile time. E-break and e-call are fairly straightforward. We have a function to handle undefined instruction encodings. If val is a bit fancy, it's how we handle conditional execution. Basically, we evaluate a specific condition on two values at runtime, and then depending on the result of the comparison, we're either going to execute the first closure or the second closure. So this is what the front end looks like. You can see how it basically looks the same as before. We're just, instead of operating on the state, we're just using the methods on the trans trait, just figuring out which registers we're reading and writing, storing the result to another register, etc. It's very similar to the interpreter we had before. So this is what the interpreter backend looks like. In the interpreter, there's no distinction between a runtime value and a compile time value. So the value type is just U32. And get register just reads from the state, set register writes to the state, add just adds to U32s. Very straightforward. The JIT compiler backend is similar, but value in this case represents a value at runtime. So what it is, it's a value is the name of a local variable in the generated RISC code. Every operation that returns a value essentially defines a new local variable. But otherwise, the actual code that we're emitting is very similar to the interpreter. Just read from the state, write to the state, add two values. And let's see how we're doing on performance. Again, the only thing we care about. It's a huge win. We are 4.8 times faster than before. We are now executing about 12 x86 instructions for each RISC-V instruction, which is good, but still pretty bad. So what's the problem? Well, let's run it under a profiler. It turns out we are spending 80% of the time just looking up what is the function for the next block to execute. Oops. So how do we fix this? Well, we need an optimization called block linking. So if the target of a jump instruction is known at compile time, then we know that the lookup will always return the same value. So we just cache it. Just cache the result of the lookup in the generated code, and then we can just, the generated code can then just directly return the address of the next function from the cache. We need to make a small change to how the emulator main loop works, in that the generated code needs to return the address of the next function to execute. So the emulator main loop then really just calls a function and then calls the function that it returned and calls the function it returned infinitely. In case the target of the jump is not known at compile time, the generated code is responsible for performing the lookup. So this is called block linking because one block of translated code is essentially directly linked to the next one. In order to determine whether a value is a constant or not, we need to keep track of a bit more information in the JIT compiler. Instead of a value just being the name of a local variable, it's now either the name of a local variable or a constant value. And in the arithmetic operations like add, we detect if the two operands are constant, and if they are, we emit another constant. So essentially propagating constant values across operations. And this is what the generated code looks like. At the top, you have the actual generated code, which ends with a jump to constant address 30. We have the jump cache, which is just a static variable. And initially, this jump cache points to a resolver function. The problem is when we generate the code, we don't know in advance, we don't necessarily in advance, the target of the jump may not have been translated yet. And that's what the resolver is for. So the resolver is only called once, the first time the jump cache is used. And it just performs a lookup and updates the jump cache to point to the resolved address. You'll note that this uses unsafe code and static mute. This is fine in this case because our emulator is single-threaded. It will be a problem if we add support for multiple threads, but that's a whole can of worms that we'll discuss later. So let's look at our performance results. We are now two times faster than 4, so 10 times faster than the interpreter. We're down to 17 x86 instructions per RISC-V instruction, which is, 17 x86 instructions for all 6 RISC-V instructions, so in about 3 x86 instructions per RISC-V instruction. This is pretty good. However, if we look at the profiling results, we notice something a bit disturbing. We're spending 13% of our time actually in RISC-C just compiling the code. This is pretty huge. So really, we should have seen this coming. Abusing RISC-C like this is not a proper JIT compiler. So let's try to get an idea of what the cost of translation is. Instead of taking the 1 billionth number in the Fibonacci sequence, let's try getting the 10th number. At this point, the cost of execution is basically 0. It's all in the cost of translation. On the left, you have the interpreter, which is very fast. And on the right, you have the JIT compiler, which is less fast. So in this example, the JIT compiler is translating 7 blocks of code. And it's taking almost 400 milliseconds to do it. That's about 57 milliseconds per block. This is huge. You don't realize it here. It's only 400 milliseconds, a fraction of a second. But a real application like, say, trying to run Firefox will have millions of blocks of code, which I think is going to take, I didn't do the exact math, but I think it will take multiple hours to actually translate all of those blocks. Very poor user experience. So we don't actually need the full power of RISC-C here. Most of the work in parsing the Rust code, type checking it, is really wasted. We only really need the compiler backend. So let's use CraneLif, which is a low-level code generator written in Rust. It's similar to LLVM. Here on the right, you can see an example function in CraneLift IR. It's constructed using API calls. So this down here is basically the implementation of the add operation in the CraneLift JIT backend. And let's look at the results. So apparently adding a CraneLift JIT backend is a 1,000 times speed up for the case of the 10th number in Fibonacci sequence. And it's a 1.2x speed up for the 1 billionth case. This is entirely due to the reduced time spent compiling code. However, if we look carefully, we can see that the code generated by CraneLift isn't really as good as the one generated by RISC-V. We are now executing 22 billion instructions, whereas the RISC-V JIT was only executing 17 billion instructions. We're still overall faster because the number of instructions doesn't, x86 has these big out-of-order CPUs, the number of instructions doesn't necessarily map to one-to-one to the execution time. But anyways, this is a pretty good speed up. So that's all that I've implemented so far for this emulator. But let's take some time to discuss how we can make it even better in the future. Now, if you recall, we're executing an average of about 2.5 x86 instructions per RISC-V instruction. We can further improve that by using a custom calling convention. Rather than returning the address of the next function to execute and having the main loop continuously execute it, we could try having the generated code directly jump to the next block to execute. Unfortunately, this requires support for tail calls. Otherwise, we're going to continuously increase the amount of stack space that we use and eventually run out of stack space. Tail calls aren't supported by either Rust or CraneLift. There is some support for it in LLVM. So there is an RFC in Rust for this. There is an RFC in CraneLift for this. So hopefully we'll see something soon. So another bonus is that once we do this, we can actually pass bits of the emulator state directly as arguments to the next function, essentially passing them in registers and avoiding the need to read these values from the state in memory in the generated code. So if you recall, in the original version, the emulated state is a mutable reference. It's stored in memory, and we need to read and write values to it all the time. But here, we can just keep everything in registers and pass them straight on to the next function. So something that we've very conveniently ignored so far is that memory accesses can actually fail. There's various reasons for this. Usually it's because of page permissions, or if the operating system hasn't finished loading your program from this, it's just accessing an address is just going to create a page fault, which the operating system handles and loads your thing from disk and then loads your program from disk and then resumes execution. Anyways, in response to a failed memory access, the CPU will generally transfer execution to a fault handler. So we need to be able to emulate this. And we do this by changing all operations on the trans trait that access memory to return result. So this is mainly fetching an instruction and loading and storing to memory. In the interpreter, all of these can return an error if the memory access fails. And we basically just throw the question mark at it. It's an early return, and we just stop executing the rest of the instruction. That doesn't really work for the compiler. It works for the instruction fetch part. So instruction fetch will return an error. However, at runtime, the fault only happens at runtime, so the compiler is responsible for generating the necessary code to handle failing memory accesses and aborting execution of the current block of code. And another thing that we've also very conveniently ignored is that instructions are just bytes in memory, which means that you can take a store instruction and just overwrite your own code. It's called self-modifying code. Please don't do this. But it can happen, and we need to be able to support it. The problem is, well, we've basically been ignoring that, and if you modify the code in memory, then now our JIT compiled code no longer reflects the actual instructions that are in memory. It's incorrect. So this is a bit tricky to handle. On RISC-V, so physical CPUs have the same problem because they have an instruction cache which is not updated when you write data to memory. So you are supposed to use this ifence instruction on RISC-V after modifying code. And if you don't, it's according to the CPU manual, it's undefined behavior. Don't do this. So there's two ways in which we can handle this. We can, if we detect, if a RISC-V ifence instruction is executed, we just delete all of the translated code that we've generated so far. Another possibility is more fine-grained invalidation, where we detect changes to the code memory and only delete translated code blocks for the memory that has been modified. So when execution gets back to them, they get retranslated. Multiple threads just makes everything harder. Remember jump caches from before? Yeah, we need to fix those. They no longer work. We need to use atomic operations for those. Hash table lookups, we've solved them in the case where the branch target is known at compile time, but unknown targets are actually very frequent in real code. So this still needs to be fast, and we can't really afford to lock the whole hash table every time we need to do a lookup. So we really want a lock-free hash table. We need to take special care of what happens if two threads translate the same code at the same time. Or, even worse, if one thread is translating code and then another thread modifies the code that's just been translated. All sorts of fun stuff happens. Cache invalidation is also tricky. We need to safely, so if we modify some code, it means we need to invalidate the translated code. But what if another thread is actually executing the code that we're trying to invalidate? It's all sorts of mess. You need some sort of garbage collector to only free the code once you're sure no threads are still executing it. Another thing that we can add is tiered compilation. So the interpreter works really well for code that is rarely executed. And the JIT compiler works well for hot code that is executed many times. Can we combine these two advantages? Well, yes, we can. We can just use the interpreter by default, but add some counters. And if we detect that the same code is executed many times and this counter reaches a threshold, we can then switch to JIT compilation just for that particular piece of code. And this allows us to get the best of both worlds. It also allows us to run JIT compilation in the background, because while the code is compiling, we can still continue execution using the interpreter. This is great because normally most systems these days have more CPUs than they know what to do with, so running more stuff in the background is always great. Finally, the holy grail of binary translation is not having to translate at all. We want to be able to load already translated code straight from disk and just run it immediately. And there's two general approaches to doing this. We can just do a first run with JIT compilation and then save the results to disk. so it can be reused in the further run. Unfortunately, this still suffers from poor performance in the first run of the application, and first impressions are important. A better way of doing this is to run a static analysis pass on the actual application binary, just when it's installed. And this static analysis is trying to locate all of the code blocks in the binary. Remember, the binary is just a bunch of bytes. In machine code, there are no functions, there are no types, there's nothing, there is only bytes of code and jump instructions that jump between them. So a nice thing about that is that you can actually reuse the trans trait interface for the static analyzer. Remember, because the static analyzer also needs to decode the instructions and essentially just run a simulated execution through the binary to just try to find all of the possible jump targets. Once all of the blocks of code have been located by the static analysis pass, we just compile them, just like with the JIT compiler using either crane lift or, if you're desperate, RISC-V. So in the end, there are an infinite number of variations and optimizations for binary translation, and it's still a very active research area. Thank you very much for listening to my talk. Here's another link to the slides in the GitHub repository with the emulator. You can try it out yourself. Any questions? Where is the microphone?
Thanks. Yeah, great talk. Well, two, but hopefully very quick questions. One is, I noticed you're using crane lift there. Is that something you would recommend in production over something like LLVM? And also, I noticed you're using perf instruction counters. Are there any other kind of performance tooling tips and tricks you'd recommend?
So I didn't quite catch the first question, but the second one. Perf is a tool that only works on Linux. I know there are equivalent tools on Windows and Mac, but I don't know what they are.
Okay, so yeah, the first part then was, would you recommend crane lift for a production system over something like LLVM for code generation?
I think crane lift is production quality. It's certainly it's good enough to use in production. If you want the absolute maximum performance, and this is what I'm doing at my startup. If you want the absolute maximum performance, you really want to write your own compiler backend, custom calling convention and all that.
You've touched upon making all of this multi-threaded. What are the best crates available for like a lock-free data structure, hash maps, B trees, and so on?
So Crossbeam is pretty good, but I'm not using it. I have plans to write my own lock-free B tree and lock-free hash map. If I ever get around to that, I will definitely release them as open source. There are several concurrent hash maps. I cannot remember the name of it off the top of my head. Dash map, yeah. But those, I believe, still use locks. They just use sharded locks. So instead of a single lock for the whole hash map, you have 8 hash maps, each with their own lock. And depending on the hash of your value, it uses one of those 8 maps. But for the issue of garbage collection, Crossbeam Epoch is an epoch-based garbage collector, and it's very similar to what I'm using.
Hi there. Yes, very nice talk. Thanks very much. And yes, I've been writing binary translators since the 80s. Things like the PGC 7600, which was at one time the fastest CPU on the planet. It's Clive Sinclair. And yes, absolutely. So one thing you touched on was the tail call optimization, which does seem to work quite well in Rusty. Generally, LLVM tends to default to using tail for its final call, and so if you're writing threaded interpreters, then tail call is quite a good optimization for that. There is no var goto in Rust, so.
Yes, there are issues that are blocking tail call support, but I think it may be possible to overcome them with sort of restricted tail call support, where you can only tail call to a function with the same signature as the current function. I think it might be possible. There might be a path forward for adding that to Rust.
Yeah, so mostly in my book, I mostly use similar tail calls, so the signature is exactly the same, and keeping the number of parameters limited as well. So if you want to translate, by far the best method is just to poke bytes into memory and run them. It's not going to be anything faster than that. So I guess that's where you're going in the end.
Yes, and additionally, there's all sorts of other optimizations you can do that are well known, but I didn't have time to cover in the talk. Like there's types of jumps where the address is not a constant that you can that you can actually optimize, because function calls and returns are easy to optimize, because while in the translated code you don't know where you're going to return to, but it's always going to return. The caller knows where you're going to return to, and you can keep a stack of predicted return addresses. Instead of jump caches, what you'd use in a real production system is directly patch the jump instruction using code patching. Hence, another reason why you'd want a custom backend.
Hi, thanks again. You mentioned the necessity for garbage collection.
Yes.
So my experience is that you don't necessarily need to use garbage collection for something like that. Like the concept.
It's technically not called garbage collection. It's lock-free memory reclamation.
Yes. So like.
I call it garbage collection because it's easier for people to understand.
Yeah. So I've been wondering about how difficult it would be to do something like hazard pointer implementation in Rust, and the delayed memory, as you said, delayed memory reclamation. Is that something you have experience with?
So it's actually quite simple to implement. So not hazard pointers, but epoch-based reclamation is relatively simple to implement. I think by implementation is maybe 50 to 100 lines of code. Basically, well, I'm probably not going to go into the exact algorithm, but Crossbeam Epoch has an implementation of this, but it's a bit complex since it uses a lot of lock-free tricks to improve performance. In the case of binary translator, I just keep track of when was the last time every thread in the emulator, when was the last time each of them reaches a save point. And if every thread has reached a save point since a particular object was free, that means no thread is using it anymore.
Cool.
That's a very quick and dirty overview of the actual algorithm.
Thank you. One thing I was wondering, for example, we saw box 86, which uses a method of intercepting syscalls or library calls and using native libraries when it's possible. Now we know that most of this high-performance code will either rely on libraries or will reuse code. statically, basically compiling it in. Have you seen any advantages with applying that method? You mentioned caching of pre-converted, pre-translated code. How about if we see a static compiled OpenGL inside, for example? We patch that with a call to the system's dynamic OpenGL.
You can do that. So first of all, this works. This kind of library interception, basically intercepting calls to emulated libraries and redirecting them to native libraries. It only works if you are translating from a 64-bit target to a 64-bit target, or from a 32-bit to a 32-bit target. It does not work if you're translating from a 32-bit target to a 64-bit target. I have tried. It is not possible to make it work reliably.
Windows on Windows 64 was a bit of a big hack there, right?
Well, Windows 64 doesn't actually do that. What they do is essentially system call level interception. They only, so that on Windows you have separate copies of the 32-bit libraries and 64-bit libraries. And it's only at the system for NTDLL that translates the calls to 64 bits. And that's doable, but anything more complex than that is not really possible. So even Box86 is an example. There's Box86 and Box64. Box86 does 32-bit x86 to 32-bit ARM, and Box64 does 64-bit x86 to 64-bit ARM. There's no 32-bit x86 to 64-bit ARM.
Hi, I have two questions. The first is, you're translating from RISC-V that has very few instructions to, say, x86 that has thousands of instructions. Do you actually have cases where you translate the function to something and it's much, much more efficient just because you're using very fewer instructions, in fact?
So that's something for the compiler backend to do, and it is possible for the compiler backend to generate smaller code in some cases. The problem is, and instructions sets like x86, like an add instruction on x86 will add two numbers, and it will also set the flag registers. In practice, you only care about one of these two, but when you're writing an emulator, you don't know which one of them is important, so you need to calculate both. So usually the translated code has more instructions than the source code.
Yeah, and I had a second question, which is, suppose you have the original code and, say, debug information about it, or even the source code. Would that help sometimes?
If you have the original code, just recompile it. It's always going to be faster.
Well, we all know that that's not true, though. Sometimes you recompile for another architecture, there can be horrible hacks in the code, or it may not even compile for any other compiler.
I see you are a C programmer. Yes. That's true, and the debug info, it's basically only useful, in my experience, for static analysis to locate the blocks of code, because it tells you where functions begin and end. Apart from that, it's not really useful. As I said, just recompile it if you want actual decent performance, but otherwise the best you can do is sort of ahead of time translation.
Any more questions?
Hi, thank you so much for the talk. So, as was mentioned before, the RISC-V is a relatively simple instruction set. In the more widespread instruction sets, like Intel, if you're doing translation from Intel to ARM, you have not only a lot of instructions, they also do the same job differently, meaning that if you have, for example, SIMD instructions in Intel, the ARM instructions are ever so slightly different. And so my first question is how do you handle these instructions that do similar things but semantically can be different in two processors?
So first of all, I want to make a slight note about the trans traits. It's if you want maximum performance, you need to tailor the trans trait for the destination architecture or the source architecture. And then if the behavior is different, well, then you have to live with that. You have to emulate it. You don't have a choice. Unless you want to cheat and rely on things like the fact that nobody actually cares about fully important exception flags and just not emulate those properly. Nobody cares about non-default rounding modes. Really, nobody.
Right, and my second question is, so am I right to assume that to write any translator or emulator, you not only need to know the specification of the processor, you also need to know all the bugs it has implemented. Like for instance, there has been a lot of speculation about M1 processors, which has specifically the very specific memory mode, which is only originating from Intel processors, just because it needs to emulate it.
Yes, that is. How should I put this? It depends on. So you emulate. The goal of emulation is to run applications that you care about. If applications don't rely on this bug, you don't need to emulate it.
Makes sense.
You're talking about the TSO bits that's on the M1, for which changes the memory ordering to match the one used on Intel. Unfortunately, some applications do rely on that, and you either have to rely on a hardware feature like Apple did, or basically turn every load and store in the program into a load acquired and store release.
Thank you.
Got time for one more question?
Thank you for the talk. I really enjoyed it. I'm just curious, is hardware being built with binary translation in mind? And what are examples of optimizations there?
Hardware has already been built with binary translation in mind and has been for many years. The NVIDIA has NVIDIA released I think the Nexus 9 tablet was based on a CPU called Project Denver, which basically translated ARM code into an internal instruction set using a binary translator. This was used by, so Transmeta many years ago did a similar thing for x86 CPUs. There are probably others that I can't remember off the top of my head, but it has already been done before.
Cool, thank you.
Please give one last round of applause for Amanieu.